Good morning and welcome to our third lecture on statistical mechanics. I have listed the results which we have seen in the last two lectures. We have defined beta as dou by dou E of log omega at constant n v and E equal to E bar, and eta as dou log omega by dou v at constant n e and v equal to v bar, and zeta, that is dou by dou n of log omega at constant ev and at n equal to n bar. Now for thermal equilibrium we have seen beta 1 is equal to beta 2, mechanical equilibrium means eta 1 equal to eta 2, and chemical equilibrium is reached when zeta 1 is equal to zeta 2 for the two systems. We have also shown the Boltzmann entropy relation, which is S equal to K log omega. And while discussing the contact with thermodynamics, we have seen beta was equal to 1 by kT, eta was equal to P by kT, and zeta is minus mu by kT. And hence, beta 1 equal to beta 2 means T1 equal to T2. Eta 1 equal to eta 2 means P1 equal to P2. And this zeta 1 equal to zeta 2 means mu 1 equal to mu 2. So the conditions for thermal equilibrium, mechanical equilibrium, and chemical equilibrium as seen by statistical consideration, and as we know from thermodynamics, are identically the same. Now, combining these results in the foregoing discussions, we arrive at the following recipe, following method for deriving thermodynamics from a statistical beginning. So from statistical considerations, we can derive thermodynamic quantities in the following way. First step will be to determine for the macro state defined by n, v and E of the given system the number of all possible microstates accessible to the system, and let's call this omega, which is a function of n, v and E. And the second step will be then the entropy of the system in that state follows from the fundamental formula, which we have written as the Boltzmann entropy relation, S equal to K log omega. As omega we have derived in step A, we have determined what is the value of omega for a given macro state of the system. So the entropy of that system in that macro state can be found using this equation, S equal to K log omega. One should keep in mind that K is Boltzmann constant, and that is universal constant. Now, while the leading intensive parameters, which are temperature, pressure, and chemical potential, are given by these quantities. You see, dou S by dou E equal to 1 by T, dou S by dou V equal to P by T, and dou S by dou N equal to minus of mu by T. From this relation here, we get beta, which is 1 by kT, equal to dou of log omega by dou E at constant n and v. So that is equal to, or that leads to, if you write 1 by T equal to dou K log omega by dou E at constant n and v, and K log omega from here, K log omega is S, that is entropy. So we get 1 by T equal to dou S by dou E at constant N and V. That is what we have for 1 by T over here. Similarly, the other relations can also be derived from here. This relation is eta equal to dou log omega by dou V at constant N and E. And eta, as we have seen, eta is P by kT. So this is P by kT. Or if you write P by T, that is equal to dou by dou V of K log omega at constant N and E. But K log omega again is S. So for P by T we obtain dou S by dou V at constant N and E, which we have over here. P by T equal to dou S by dou V at constant N and E. Similarly, the third one, this relation can also be obtained from here. You see, this is zeta. If you write it over here, zeta equal to, from here it is minus mu by kT, which is equal to dou log omega by dou N at constant E and V, or if you take this K over there, mu by T with a minus sign becomes dou K log omega by dou N at constant E and V, but K log omega is S, so dou S by dou N at constant E and V is equal to minus mu by T. So that relation is over here, dou by dou N at constant E and V is equal to minus mu by T. So we get all these three relations from here. We can express the quantities pressure P, the chemical potential mu, and the temperature T as derivatives of the energy E. We have seen that P by T is equal to dou S by dou V at constant N and E. We also know that dou S by dou E at constant N and V is equal to 1 by T. So we get P equal to dou S by dou V at constant N and E divided by 1 by T. So that is dou S by dou V at constant N and E divided by, we are writing 1 by T from here, dou S by dou E at constant N and V. So P equal to, let's write dou S by dou V at constant N and E divided by dou S by dou E at constant N and V, and that will be equal to minus of dou E by dou V at constant N and S. To obtain this result, we are using the well-known result of partial differentiation, which is dou X by dou Y at constant Z into dou Y by dou Z at constant X into dou Z by dou X at constant Y is equal to -1. So we have made use of that formula over here, and we obtain P equal to minus dou E by dou V at constant N and S. So let's write it over here. Dou E by dou V at constant N and S is equal to minus P. Similarly, we have shown that minus mu by T is equal to dou S by dou N at constant E and V. And again, we'll use 1 by T equal to dou S by dou E at constant N and V. So mu equal to minus dou S by dou N, dou S by dou N at constant E and V divided by 1 by T, and we substitute for 1 by T and we obtain dou S by dou N at constant E and V divided by dou S by dou E at constant N and V with a minus sign here. So that is equal to, you see, dou E by dou N at constant V and S. So you obtain mu equal to dou E by dou N at constant V and S. We have also shown P equal to minus dou E by dou V at constant N and S, and T we can write equal to dou E by dou S at constant N and V. The evaluation of pressure P, the chemical potential mu, and the temperature T from these formulae indeed requires that the energy E be expressed as a function of two quantities N, V and S, because then only we can differentiate E with respect to V, N and S to find pressure, mu and T respectively. This should be possible, at least in principle, once S is known as function of N, V and E. We have already mentioned that S will be a function of N, V and E. Once we know this S, it is possible to write E as a function of N, V and S. And once we write E as a function of N, V and S, we can find out mu, P P and T from this relation. Now these relations, these three relations, which we have found now from statistical consideration, can be found from thermodynamic relation also. If you write dE equal to TdS minus PdV plus mu dN. This thermodynamic relation will also give rise to these three equations. You see, from here, from this equation, we write dou E by dou N at constant V and S. Then what do we get? V is constant, so PdV is 0. S is constant, so TdS is 0. So dou E by dou N will be mu. That is our first relation here. Now from this equation only, dou E by dou V at constant N and S. Constant N in this term is 0 dN, and constant S, so TdS is 0. So dou E by dou V from here will be minus P, exactly as we have over here. And similarly, dou E by dou S at constant N and V will be, N and V are constant, so dN is 0, dV is 0. So dou E by dou S at constant N and V will be equal to T. That is the third equation here. So these three equations which we had derived from thermodynamic considerations are also directly derivable from, rather these three relations, we are redoing it. So we find that these three relations for mu, P and T, which we have found through statistical considerations, can also be directly found from an equation in thermodynamics, which is a well-known equation in thermodynamics, directly. So the results which you obtain from statistical considerations and the result which we know from thermodynamic studies are exactly the same. The rest of the thermodynamics will follow straightforwardly. For instance, the Helmholtz free energy F gives free energy G and enthalpy H we can find as follows. Helmholtz free energy F is equal to E minus Ts. The Gibbs free energy G, that is equal to F plus PV, or that is E minus Ts plus PV, and enthalpy H is given by E plus PV, and that is G plus Ts. So say for F, for Helmholtz free energy F, what do? We find omega, and once we find omega, we use k log omega to find S, and as S is found in terms of N, E and V, we find E also from here, and hence as temperature is found from E or from S, so all these quantities E, T and S are found once we find omega. Similarly, for Gibbs free energy G, all the relevant quantities can be found once we find omega. So what we see is the basic task now is to find what is the number of microstates available to a system in a particular macrostate. We will keep in mind that we'll be discussing the systems in equilibrium. Systems which are not in equilibrium, that we will not consider right now. The remaining two important quantities in thermodynamics are CV and Cp, where Cv is the specific heat at constant volume and Cp is the specific heat at constant pressure. Now Cv is T dou S by dou T at constant N and V. Basically this is dou E by dou T at constant N and V. So once we find E, we can find Cv. Similarly, Cp is T dou S by dou T at constant N and P, and so that is dou by dou T of, and that is Se plus Pv, because volume is not constant here. So at constant N and P, which we can write as dou H by dou T at constant N and P. To illustrate the approach developed up to now, we shall now derive the various thermodynamic properties of a classical ideal gas composed of monatomic molecules. The main reason why we choose this highly specialized system for consideration is that it affords an explicit, though asymptotic, evaluation of the number of the microstates omega as a function of N, V, and E. This example becomes all the more instructive when we find that its study enables us, in the most straightforward manner, to identify the Boltzmann constant K in terms of other physical quantities. Moreover, the behavior of this system serves as a useful reference with which the behavior of other physical systems, especially real gas, can be compared. And it's a fact that in the limit of high temperatures and low densities, the ideal gas behavior becomes typical of most real gases. Before we take a detailed study of this case, it is important to make a remark which applies to all classical systems composed of non-interacting particles. Now this remark, which we are going to make, is related to the explicit dependence of the number omega on V. So how does omega depend on V? We'll talk about that, and hence to the equation of state of these systems. Now, if there does not exist any spatial correlation among the particles, that is, if the probability of any one of them, any one of the particles, being found in a particular region of available space is completely independent of the location of the other particles, then the total number of ways in which n particles, capital N, can be spatially distributed in the system will be simply equal to the product of the number of ways in which the individual particles can be accommodated in the same space independently of one another. With N and E fixed, if N and E are fixed, each of these numbers will be directly proportional to the volume capital V, which is the volume of the container. If V is the volume of the container, the total number of ways in which N particles can be arranged within this volume will be proportional to nth power of V, which will be proportional to V to the power N. You see, the number of ways in which one particle can be placed within the volume V will be proportional to the volume V. This is number of ways in which a single particle, may be placed or may be arranged in the volume V. This number will be proportional to the volume V. Now, as we have mentioned earlier, that presence of one particle does not affect the presence of other particle. That means there is no spatial correlation between the particles. So the probability of any one of them being found in a particular region of available space is completely independent of the location of the other particles. That means if you take the second particle, the number of ways in which that particle can be placed within the same volume V will also be proportional to V. So for second particle, the number of ways will also be proportional to the volume V. So what is the probability, or what is the number of ways in which the two particles can be arranged? That will be V to the power 2. You see, number of ways two independent particles may be arranged within the volume V will be the number of ways in which one particle can be arranged multiplied by the number of ways in which the second particle can be arranged. So this will be proportional to V to the power 2. Hence, the number of ways in which N particles may be placed within this volume V will be proportional to V to the power N. And this number of ways in which N particles can be arranged within a volume V is the number of microstates for that system. So number of microstates available to a system of N independent particles within a volume V will be proportional to V to the power N. So number of ways in which N particles may be arranged within a volume V will be proportional to v to the power n, provided all these particles show spatial independence. Which means the spatial independence means the presence of or the probability of a particle being found anywhere within that volume has nothing to do with the presence of other particles in that volume. Now this number of ways in which n particles may be arranged is basically the number of microstates. So number of microstates omega, which in general is a function of n, v and e, is proportional to v to the power n. Now we have seen that p by t is equal to a constant dou log omega by dou v at constant n and e, and if you use this for omega, we get k n by v. That constant of proportionality over there is merged with the constant, Boltzmann constant. So log omega, omega is v to the power n, so log omega becomes n into log v, and when we differentiate it with respect to v, you will get n into 1 by v. Now if the system contains n moles of gas, then capital N is equal to small n into A, and then we get P by T equal to K N A by V, or PV equal to N K into A multiplied by T, and this K into A we take as R, a constant, so PV equal to nRT, and that is a well-known equation which we call ideal gas equation. Ideal gas equation. Nothing new over here. We know this equation very well, PV equal to nRT. But the approach that we have taken to arrive at this equation is new. If you remember, before that, earlier, what we used to do was that we mentioned Boyle's law, Charles' law, Gay-Lussac's law, and then we derived this equation, PV equal to nRT, for an ideal gas. Just by taking these three laws, we had written it. Now we are actually deriving it from statistical consideration. We have just mentioned that omega will be proportional to v to the power capital N, if capital N is the total number of particles present over there. And from this statistical consideration, we arrive at this equation, PV equal to nRT. So that is a true derivation of this equation. Before that, we were just mentioning the laws and we were combining them to find this equation. So, for any classical system composed of non-interacting particles, the ideal gas law holds. For deriving other thermodynamic properties of this system, we require a detailed knowledge of the way the quantity omega, this omega, depends on the parameters n, v and e. The problem, that means, essentially reduces to determining the total number of ways in which equations sum over I and I epsilon I equal to E and sum over I and I equal to capital N may be satisfied. In other words, we have to determine the total number of ways, independent ways, of satisfying the equation sum over I, or let's say R, from 1 to 3n epsilon R equal to E, where the epsilon R are the energies associated with the various degrees of freedom of the system of n particles. The reason why this number should depend upon the parameters n and E, that is capital N and capital E, that is obvious. Apart from obvious dependence of the number of microstates on capital E and capital N, the number would also depend upon the spectrum of values. Spectrum of values which the variables epsilon R can assume. It is through this spectrum that the dependence on V comes in. So let's see how that dependence on V comes in. We know that the energy eigenvalues for a free non-relativistic particle confined to a cubical box of side length L, under the condition that the wave function psi vanishes everywhere on the boundary, are given by epsilon function of nx, ny and z will be equal to h square by 8m L square, nx square and y square plus nz square, that you might have seen in quantum mechanics when we consider particle in a box, or you will see in forthcoming classes in quantum mechanics. Nx and ny and nz are integers, and that can take any value 1, 2, 3 and so on. H is Planck's constant and m is the mass of the particle placed in a cubical box of side length L. Epsilon is the energy eigenvalues, the energy eigenvalues of a free non-relativistic particle confined to a cubical box, of side length L, under the condition that the wave function psi r vanishes everywhere on the boundary of the box. As side length of the cube is L, so total volume of the cube V will be L cube, So for L square, we write V to the power 2 by 3. So we write epsilon as a function of nx, ny, nz equal to h square by 8m v to the power 2 by 3 nx square plus ny square plus nz square. The number of distinct eigenfunctions, the number of distinct eigenfunctions, which we call microstates, for a particle of energy epsilon, for a particle of energy epsilon would be equal to the number of independent positive integral solutions, positive integral solutions of the equation nx square plus ny square plus nz square equal to 8m v to the power 2 by 3 divided by h square multiplied by epsilon. So this comes from quantum mechanics, that the number of distinct eigenfunctions, which we are calling macrostates as we have mentioned earlier. So the number of distinct eigenfunctions for a particle of energy epsilon would be equal to the number of independent positive integral solutions of the equation given by nx square plus ny square plus nz square equal to 8m v to the power 2 by 3 divided by h square into epsilon. Now, as this is for a single particle, we may denote this number by omega. 1 is for one particle, epsilon v. One particle with energy epsilon in the volume v. So that number, which is the number of distinct eigenfunctions, will be denoted by omega 1 epsilon v, because it is being written for single particle with energy epsilon and volume in which that particle is confined is v. As this is for a single particle, this can also be written as nr square sum over r from 1 to 3, because for a single particle there will be 3 degrees of freedom, and that is equal to 8m v to the power 2 by 3 divided by h square multiplied by epsilon. If we extend this argument to a system with n particles within volume v and energy E, omega n E v can be written as the number of independent positive integral solutions to the equation n r square sum over r from 1 to 3n, which is equal to 8m v to the power 2 by 3 divided by h square multiplied by E. So, the independent solutions of this equation, total number of independent solutions, independent positive integral solutions of this equation will be equal to the number omega. So, number of microstates for a system of n particles kept in a volume V, n non-interacting particles, kept in a volume V with total energy E, will be given by the independent positive integral solutions of this equation. So, number of microstates for a system of n particles, n independent particles within a volume V with total energy E will be given by the solutions of this equation. And what type of solutions? Positive integral solutions of this equation. So remember, omega is not this. Omega is the number of solutions for this equation. And the condition is that that solution should be for positive integral numbers. The number of microstates for a system of n independent particles kept within a volume V with energy E is given by the total number of independent positive integral solutions of the equation sum over r from 1 to 3n nr square equal to 8m v to the power 2 by 3 by h square multiplied by E. A very important result can follow or will follow straightforwardly from this equation even before the number omega is explicitly evaluated. From the nature of the expression appearing on the right hand side of this equation, we conclude that the volume V and energy E of the system enter into the expression for omega in the form of the combination v to the power 2 by 3 multiplied by E. We know omega will be function of n, V and E, but V and E enter into the expression for omega as a combination because v to the power 2 by 3 into E is present on this right hand side. So this quantity enters into the expression for omega like v to the power 2 by 3 into E. So S, which is function of n, V and E, can in our case be modified to S function of n and v to the power 2 by 3 into E. Now in a reversible adiabatic process, S, that is entropy, and N must be a constant. So for such a process, v to the power 2 by 3 into E comes as constant because S and N are constant. That means v to the power 2 by 3 into E will be constant. Then only we can say that S remains constant. So, if we derive this, if we take derivative of this equation with respect to V, we get 2 by 3 v to the power minus of 1 by 3 into E dV plus v to the power 2 by 3 dE is equal to 0. So dou E by dou V, in this case when N and S are constant, is given by minus of 2 by 3 E by V. But dou E by dou V at constant N and S we have also seen as P equal to minus dou E by dou V at constant N and S. So that from here becomes equal to minus 2 by 3 E by V. So this minus sign makes it positive, and hence we obtain P equal to 2 by 3 E by V. Now this relation gives E equal to 3 by 2 PV, and that is a well-known relation in thermodynamics. So this equation P equal to 2 by 3 EV, that is the pressure of a system of non-relativistic, non-interacting particles, and it is precisely equal to 2/3 of its energy density. E by V is energy density. So pressure P is equal to 2 by 3 E by V means pressure is 2/3 of energy density. For what kind of a system? This is the pressure of a system of non-relativistic, non-interacting particles. Now, as we have also obtained V to the power 2 by 3 into E is equal to constant, let's substitute for E from this equation. So we get V to the power 2 by 3 multiplied by 3 by 2 into PV equal to constant. We can take 3 by 2 over here in the constant, and then we get PV to the power 5 by 3 equal to constant. And obviously this is the equation for a gas undergoing adiabatic process. And remember, we have taken that example of adiabatic process, that is reversible adiabatic process. So that process is defined by PV to the power 5 by 3 equal to constant. Remember, we are taking monatomic molecules. For monatomic molecules, gamma is equal to 5 by 3. So basically this is PV to the power gamma equal to constant. You see, the power of this statistical method is that the number omega has not yet been derived. The number omega we have not found yet. But just by considering the property of omega, how does omega depend on N, V and E, we have been able to derive ideal gas equation. We have been able to derive the expression for pressure P, which comes out to be 2/3 of the energy density, and we have been able to derive the equation for the adiabatic process in an ideal gas. We should also remember that since an explicit computation of the number omega has not yet been done, these results which we have derived, P equal to 2 by 3 E by V, or this equation PV to the power 5 by 3 equal to constant, will hold good for quantum as well as classical statistics. So this can be applied to systems which can be defined classically or which can be defined quantum mechanically only. By this time we should be able to recognize the strength and the scope of this method, which we are calling statistical method, because we have seen that without using the phenomenological inferences, we are able to derive a number of equations just by considering the mathematical method. So gradually, as we develop, we will see that the method that we are going to adopt is so powerful that it finds application, in almost all fields of not only physics, of different subjects also. We'll take up the next day what is phase space and how it is used to describe a system, a statistical system.